Alright, in this video I'm going to be demoing the golden section search method, which is an one-dimensional optimization method that you can use to search for max and mins of functions. So the algorithm that I'm going to introduce for the golden section search is used specifically to look for maxes of functions, and I'm going to demo it searching for a max of this function here, f of x equals the natural log of x minus 0.1 times x squared. And I just thought it would be nice to plot that in MATLAB so that we could see what the function looks like. So I'm going to define x is equal to, I'm going to start it at a value of 0, go in steps of 0.1 to 4, and then I'm going to say y is equal to the log of x minus 0.1 times x squared, and then I'm going to plot that. So plot x comma y, and I'm going to turn the grid on. Alright, where is my function here? Oh no, this is hold on here, I need to clear an old plot here. So let's do close all and do this again. Plot xy. Hold on just a minute, I'm going to turn the grid on. Alright, so now we can see this function. It has a max somewhere here, maybe 2.25, 2.3, and so we might say let's give a lower bound of 1 and an upper bound of 3, and use that interval, pass that interval to the golden section search method, and have it search for this max of 2.3, 2.25, something like that. Okay, so that's what we want to do. So I just want to kind of remind you of the golden section search algorithm. So I have it written up here, and I just wanted to go through it. So once we have an interval, which we have a function and we have an interval now between 1 and 3. So given an interval containing a max, we found an interval for some function f of x, we need to calculate some things. We need to calculate the golden ratio. We need to calculate the golden ratio times the length of our interval, which we're going to call b. And we need to find the 2 points inside our interval x1 and x2, which are equal to x lower plus d and x upper minus d, and then f1 and f2. Now if all this doesn't sound clear, please go back and watch my introduction video on the golden section search algorithm, and these variables will become clear what they are. So once we've calculated those, then we're going to estimate a value for the optimum, the X optimum, by doing the following check. So we check if f1 is greater than f2. If that's true, then we set x1 to be the optimum. If it's not true, then f2 is greater than f1. Then we set x2 to be the optimum. The next step that we would do is we'd calculate the approximate error and check for convergence. So this is the equation for the approximate error. It gives a bound on the error, so the error can never be bigger than this. So for a derivation of this, see the book. So then we just say if this error is less than the tolerance, then we'll stop iterating. And then before we move on to the next iteration, we need to update our values for the next iteration. So one thing that we can do is we can, in order to update d, we can just set d equal to r times the previous value of d, instead of updating our lower bound or upper bound and then calculating it in terms of our lower bound and upper bound. And this is just a nice property of the golden ratio, and it allows us to avoid round off error in d. So as we know, x lower and x upper, as we iterate more and more, are coming closer and closer together around the maximum. And so they're becoming, the numbers stored in x lower and x upper are getting closer and closer to each other. And d itself is defined, you can just take this over here, let's d, remember, let's see here, d was equal to r times x upper minus x lower. So if these two numbers, x upper and x lower, are approaching each other, then this difference is going to get very, very small and can be very subject to round off error. So it's better, instead of calculating our updated value of d like this, to just use the property of the golden ratio, set d equal to r times the previous value of d. And then this avoids this subtractive cancellation where we can get round off error. Okay? So back to the algorithm here. So we're going to update d. Then if f1 was greater than f2, we're going to update our variables in the following manner. Set xl equal to x2, x2 to x1, x1 to xl plus d, f2 to f1, f1 to f of x1. And if not, then we're going to, if f1 was not greater than f2, and we have the other case where f2 is greater than f1, then we update the variables as follows. And then all we have to do is repeat steps 2 through 4. So estimate the optimum, calculate the error, check for convergence, update values. We just do that over and over. So I'm going to show you how to do that by hand for this function right here, f of x equals ln of x minus 0.1 x squared. So the very first step was we need to calculate our values between our values for x1 and x2 and the functions evaluated at those points. So I'm just going to first of all, let's say for the iteration 1, iteration number 1. Okay. Actually, before we do iteration number 1, before we even do the iteration, let's just do the setup, okay? Setup. So, the setup, we already know our x lower equals 1, our x upper equals 3. So, our d is going to, well, r is going to equal the square root of 5 minus 1 over 2. And then d will equal r times x lower, x upper minus x lower, which for this, the very first iteration, this is equal to 1.236. Alright, now we can calculate our first x1 and x2 values. So we're going to get x1 is equal to x lower plus d, which that's equal to 1 plus 1.236, which is equal to 2.236, which is actually really close to the real optimum. So we'll see that we're always going to end up keeping this one, I think, for the first few iterations. And then x2 is going to equal x upper minus d, which that's 3 minus 1.236, and that's equal to 1.764. Now we need to set f1 is equal to the function evaluated at x1. So if we stick 2.236 into this function up here, then we get a value of, let's see here, I'm just reading it off. For x1 we get 0.305. You can check this by plugging these into your calculator or into MATLAB or something. f2 equals f at x2, which this is equal to 0.256. Okay, now we're ready to do iteration 1. So this was all just set up, okay? So now we're going to jump in and do iteration 1. So iteration number 1. So what we're basically going to do is we're going to say, okay, is f1 is greater than f2 in this case, so that means we're going to set our optimum X optimum equal to x1. Alright, so now we would want to calculate the error. So the next step would be calculate the error using our equation. Let me see if I can find it here. So this was our equation for the error right here. So this is the next step. So this is the first step in our iteration. Estimate X optimum. We did this very first step, which was just the setup. Calculate all this stuff. Then estimate X optimum. We did that because f1 was greater than f2. We said X optimum equal to x1. Then we calculate the error and check for convergence. I'm actually just going to skip that step and jump right to update the values for the next iteration. And so we'll skip the error checking here. So calculate error, but you would do this in MATLAB if you were writing a MATLAB function. So I'm going to skip for now and jump to the update step. So we need to update values. Okay. Alright. So the first thing we need to do is we need to calculate our new d value. So we're going to have d is equal r times the previous value of d, which the previous value of d was, I believe it was 1.236, right? 1.236. So that actually, when we calculate the new value of d, it's now equal to 0.764. 0.764. Now we've got the new value of d. Now we need to update the the other values. So first what we're going to do, because f1 was greater than f2, we're going to update the values using the set of rules for when f1 is greater than f2. So you might remember that if we had our function here, see if I can kind of draw this function between 1, 2, 3, 4. It looks something like this, right? And this is our x lower. This is our, let's see, this is 1, 2, 3, this is our x upper. And then we've got a x1 and an x2 somewhere in here. So x1, x2, alright. And it just so happened that in this case, sorry, I wrote these backwards. This is x2, this is x1. So in this case, f1 was greater than f2. So this was f1, this was f2. So this is f2. And this one right here is f1. Okay, just to make it clear. So now we're going to be, because that's the case, we're going to chop off this part of the interval right here. So this piece of the interval from xl to x2 we're going to get rid of. We're going to make a new interval that goes here. I'm going to rename xl, keep the same x upper, and then define our points in here. So that's what we're doing in this update step. Alright, so now we're going to let x lower equal x2, which is equal to, see if we can remember from up, we can just scroll up here. So what was x2? 1.764. So we get this equal to, whoops, hold on, 1.764. And then we said, okay, now we also need to update x2 needs to be set equal to x1. So x2 now equals x1, which was 2.326 right here. So x2 equals x1, which equals 2.236. And then we had x1. We're going to calculate a new x1. So our new x1 is equal to our new x lower plus our new d, which this new value, if you plug it in to your calculator, you're going to get a value of 2.528. So 2.528. Now we need to also calculate the new function values. So f1 is just get set equal to f2. So f1 gets set equal to f2. So f1 was equal to 0.305 from the previous iteration, 0.305. And then we have to calculate a new f2. Sorry, I switched this around. This should be f2 equals f1. And then our new f2 value, let me just check what it's going to be, 0.288. This is the function. Sorry, I'm writing all this backwards again. So this is f2 equals f1. and then we need to update f1. So f1 now equals the function evaluated at our new x1 value, which equals 0.288. Alright, now we're ready to jump to the next iteration. So let's kind of keep these updated values in view. So I'm going to come down here and write iteration 2. Alright, so we check and we see that F2 here has a value of 0.305 and F1 has a value of 0.288. So now we can say F2 is greater than F1. So because that's the case, what we're going to do is what are we going to set our X Optimum value to be? X Optimum is now going to be set equal to X2, which is still equal to 0. It's not the function value. It's equal to 2.236. Alright, so that's our estimate for the optimum. That's step 2 from the algorithm. We're repeating that. Step 3 was calculate the error, which we're going to skip the error again, and so we'll jump right to the update. So now we're going to say update values. So first thing we'll do is we'll set D equal to the previous value of D, R times D. So R times the previous value of D up here was 0.764. We got 0.764, and this gets, plug that into your calculator. You should get a number of, let's see here, 0.472. 0.472. Alright, now we need to update our values for and this time, last time we updated XL, but this time we're going to be chopping off the right hand portion, so we're going to set our X upper is now going to be set equal to X1, which X1 was 2.528. 2.528. And now we're going to update X1. So X1 is going to be equal to X2, which up here X2 is 2.236. So this is 2.236. And then we're going to calculate a new X2 value. So we're going to get X2 is equal to our new X upper value minus D, which this gets set equal to 2.056. 2.056. And we need to update F1 and F2. So in this case we kept F2, so we got to set F1 equals F2. Well, up here we have F2 equal to 0.305. So that gets to set equal to 0.305. And then our new F2 value we have to calculate. So we get F2 equals the function evaluated at this new X2 value right here. Which if you plug that into the natural log of X minus 0.1x squared, we get a value of 0.298. Okay, I think so. Now we have all these updated values. Now we can jump ahead and do the third iteration, which we can come up here and say iteration number 3. So we check up here and we say, okay, F1 is 0.305 and F2 is 0.298. So now we have, again, the case F1 is greater than F2. So that means we set X Optimum equal to X1, which is X1 up here, 2.236, 2.236. Alright, and I'm just going to say that even though this hasn't changed, the error is going to be getting smaller. And let's say we provide an error tolerance such that now when we calculate the error, so error is less than the tolerance. So we break, so we stop. Really, I don't know if that's really true. I'm just saying I'm only going to do 3 iterations. But if we wanted to keep going, if that wasn't true, then after we calculate the error and did the check, and we still needed to keep going, we'd update our variables again. Update variables. And then we go back up and do another, and then we do another iteration. So hopefully that makes this algorithm a little bit more clear. To start off, you have to calculate these things first. Then if you were writing code, you would start a loop, and in the loop you would do this check and assign the value for X Optimum based on that check. Then you would calculate the error, check for convergence, update the values for the next iteration, and then repeat steps 2 through 4. That just means that's the end of the for loop, and you jump back up in and you reiterate. So steps 2 through 4 would be inside of a loop, for loop or a while loop. So hopefully that makes it a little bit more clear how this algorithm works, and you have a better idea having actually used a real function and done a few iterations by hand. So I will see you in the next video and talk to you then.